What is a beam splitter for photonic quantum computing? Imagine a device that can take a single beam of light and split it into two. This is exactly what a beam splitter does, and it plays a vital role in photonic quantum computing. In this fascinating field, light is not just light, it carries information in the form of quantum bits or qubits. A beam splitter is an optical device that partially transmits and partially reflects incoming light. This means that when a beam of light hits it, some of the light continues on one path, while the rest takes a different route. The ratio of how much light is transmitted versus reflected can vary based on the design of the beam splitter. One of the key features of a beam splitter is that it introduces phase shifts between the transmitted and reflected light. This phase shift is essential for creating interference effects, which are crucial for performing quantum operations. In photonic quantum computing, qubits are often represented by single photons. These photons can be manipulated using beam splitters to create quantum superpositions, where a photon can exist in multiple states at once. When photons enter a beam splitter, they can end up in a superposition of both output paths. This behavior is fundamental for operations like entanglement, which is when two photons become linked in such a way that the state of one instantly influences the state of the other, no matter the distance between them. A fascinating phenomenon associated with beam splitters is called Hong-Ou-Mandel interference. When two identical photons approach a beam splitter from different paths, they tend to exit together from the same output port. This effect is not random. It occurs with specific probabilities and is used to generate entangled states and implement quantum gates in photonic circuits. In practical applications, photonic quantum computing systems often use networks of beam splitters alongside phase shifters and single photon sources. These setups create interferometers that can perform complex quantum operations. Since photons do not interact strongly with each other, beam splitters, when combined with measurement techniques, enable the creation of probabilistic entangling gates. An example of such a gate is the controlled NOT gate, which is essential for universal quantum computing. There are two main types of beam splitters. Free-space beam splitters, like plate or cube types, are commonly used in experimental setups. On the other hand, fiber-based beam splitters are integrated within optical fibers or photonic circuits, making them more suitable for scalable quantum devices. In summary, beam splitters are key components in photonic quantum computing. They split and recombine light to create quantum superpositions and interference effects. These effects allow for the manipulation of photonic qubits, the generation of entanglement, and the realization of quantum logic gates. This makes beam splitters an essential part of the architecture in photonic quantum computers.